programmable computers were invented by the crafters. And here's a picture of a knitting pattern. And I don't know how many of you in the audience can knit, but if you can't, I'm going to bet that this looks like gobbledygook code to you. And in a way, it is. It's code. It's a code to tell the knitter what to do. And in the same way that we can machine the mechanism can either be up or down, similarly in a knitting pattern, there are two types of stitch, which is either called a purl or a knit. Now, if I write a knitting pattern, I could say purl, 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 knit, knit, purl, 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 knit, 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 and that would tell the knitter exactly what to do in the pattern. But that would be very inefficient. So knitters actually invented this type of encoding to compress their knitting patterns in order to be able to make them more efficient to write on the page. So in this particular pattern here, you'll see that it's something like P1, K1 twice, P2, K5. So that means you do purl 1, knit 1, and you do those things in brackets twice, then you're going to purl 2, then you're going to knit 5. And this seems kind of obvious and simple, but this kind of one-link encoding is used all the time around the world to compress the zeros and ones that we use when we're listening to music or watching a TV show or sending a message on WhatsApp. So there we go, already invented by knitters. This is one of my favorite examples of computer science knitting. It's the idea that we can do cryptography with knitting. There are many different ways of doing this. So this particular example here is called illusion knitting. I don't know if you'll see it, but I've got a piece here. So if I hold a piece of knitting just at the front, all you can see are stripes and white and purple. But if I were to hold the same piece of knitting at an angle, then suddenly an image starts to emerge, which should say boom. And then the proper image on the screen, you can see that Albert Einstein appears if you hold it. So there's a particular way of encoding the image using the knits and the purls of the knitting, because some of them sit higher up than the others, so you only see certain stitches and then back on the side. But you can do more interesting things with cryptography in knitting. So here are two more ideas. So you could use two different colours that encode zeros and ones. And so on the left-hand side here, someone has created a secret message by converting each letter of the alphabet into binary ASCII and then knitting those into a scarf. And on the right-hand side, someone's used the dots and dashes of Morse code to be the two different colours of their knitting pattern. You could do it with the knits and purls as well, and this could make you a secret code. And during the First World War, and I think the Second World War as well, there are examples of women who went out to the front and were sitting there harmlessly knitting away like little old ladies, but actually they were encoding secret patterns into their knitting as they were spying on the Germans and sending their finished jumpers back home to the Allies where the patterns would be decoded. So there we go. So we can use knitting as a way of doing cryptography, and I'll leave it with you to think about your own ways that you could include secret messages into a knitting pattern. So now on to my next example of an object that was invented by the knitters many years before the mathematicians. So this is something called the Möbius strip. It's a one-sided piece of paper. You may think that it was named after Mr. Möbius, but in fact, it was invented by the knitters hundreds of years before. So in any knitting pattern, whenever you're knitting something circular, the first thing the knitting pattern will tell you is don't twist your stitches before you've joined them into a circle. Because it's really easy to twist your stitches when you join them into a circle and to accidentally create the Möbius strip. So I'm pretty sure that knitters knew about Möbius strips, 2,000 years or more before mathematicians figured it out in the 19th century. And if you go into any yarn shop and you tell the person selling you the yarn that you are knitting a Möbius scarf, they will know exactly what you were talking about, even if they have never done a degree in mathematics. And another example is hyperbolic geometry. So if you're looking at how shape curves in three-dimensional space, there are three different types of geometry. There's something called spherical geometry, you can have flat geometry, and you can have hyperbolic geometry. And hyperbolic geometry curves in different directions if you take different cross-sections. Now, this might seem fairly obvious to divide geometry into these three different types, but hyperbolic geometry was only discovered in the 19th century. And it was
fought over by these three mathematicians, Gauss, Bolyai, and Lobachevsky. They all fought over who invented hyperbolic geometry first. But actually, hyperbolic geometry has been around for many thousands of years, because every time you create a garment with a bit of flair or ruffling in it, you are creating hyperbolic geometry. So knitters have known about this kind of geometry for thousands of years. We've been using it to make clothing for a long, long time. It does not come as a surprise to us. And there's a wonderful book by a Latvian mathematician called Dana Taimina, who worked out how you could use crochet to create hyperbolic planes to explore that kind of mathematics. And it's a very, very simple knitting pattern that just increases the number of stitches in each round exponentially as you move outward from the center, in contrast to a sphere where you decrease the number of stitches as you move in from the center. She realized that if you knitted hyperbolic planes, they looked incredibly like organic shapes, like coral reefs, mushrooms, seaweeds, and now hyperbolic geometry is being used to model all kinds of natural phenomena. And I could give a whole talk that was just about hyperbolic geometry and crochet. You can also use hyperbolic geometry to model some really interesting phenomena. So this is a design by Professor Hinka Singer in Auckland, and she designed a hyperbolic crochet pattern for something called the Lorenz manifold, which is an object that's used to model the equations that govern how the weather and how the atmospheric currents move. So you can do some really, really complicated physics also using craft and those ideas of visualization and geometry that we learned about before. So I realize I'm coming towards the end of my 15 minutes. So there's a few things that you can do with paper as well as knitting. So you can create hyperbolic geometry from paper by inserting heptagons or seven-sided shapes into a regular hexagonal lattice, and this will create a hyperbolic surface as well. And finally, you can do some really wonderful algorithmic things with origami, where historically this was something done by artists that would just figure out the way to create a particular shape. But now you can tell a computer what shape you want to make, and using mathematics, it will come up with the crease pattern for that shape. So there's all sorts of origami that you can do now that couldn't have been done 100 years ago because of the mathematics that's behind it. And there's some really, really wonderful three-dimensional shapes that, again, I could spend an hour talking about if I had the time this afternoon. So thank you all very much for listening. That will be the end of my talk about maths and craft. And I hope I've inspired you to get out there and start some of your own craft projects and to think about the kind of maths that might be inside them. Thank you very much.